Hi, Physics 2, Mr. Janowski. This is the first part of the Chapter 32 slides, which I realized I didn't make last week. I should have made these. So anyhow, let's get started. So some definitions. Electrostatics, the study of electric charges that can be collected and held in one place. So collected and held, we're not dealing with moving charges. Moving charges is current, and that's a different thing. So you start off studying electrostatics. The key word is static. The key part of the word is static, meaning not moving. And then you have conductors. So these are materials through which electric charge can flow easily. So that's things like silver, gold, copper, steel, all the metals. Seawater is also a good conductor. Now, you also have things called insulators. So these are non-conductors, materials through which electric charge cannot flow. So rubber famously is a good conductor. Glass, oil, diamond, dry wood. Right. I'm sorry. I think I said they were good conductors. These are good insulators. Yeah, rubber is an insulator, not a conductor. And then you also have things called semiconductors. These are materials through which charge can flow, but not easily. And these ended up being extremely important in all of the electronics and the technology we started making in the 20th century. Things you can do with semiconductors. So one thing about conductors is because charge can flow, and if you know anything about charge, you probably know that like charges repel and opposite charges attract. So yeah, if you had a solid metal sphere, so a solid conducting sphere, and you touch some charge to it, the charge would flow onto the sphere, and because it wants to get away from all the negative charges here, want to get away from each other, and they're free to move because this is a conductor, they'll just distribute themselves evenly all the way around the conductor. Now, if you did the same kind of thing and you touched some kind of probe to this thing that had too many, your probe had too many electrons on it, it had a surplus of electrons, to this insulating sphere, well, the insulator can hold the charge, but the charge is going to stick where you put it because it's not free to move around. So it says ignore the slide. Yeah, this is kind of the quantum mechanical theory of how conductors, insulators, and semiconductors work. It has to do with this band gap. So in a conductor, the two bands are like the different energy levels of the electrons. So in a conductor, the electrons are filling up all of these energy levels up to here. And if you give them just a little more energy, then they're free to move into the conduction band, and they just flow. In an insulator, there's a big energy gap. So here are your valence electrons. And if you give the electrons a little extra energy, that's not enough to get them to the conduction band. So they're not going to flow. And a semiconductor, there is a small band gap. So a tiny amount of energy won't do it, but a tiny bit more might do it. So this is like more advanced material science stuff. But yeah, some of you are going to go into STEM. You may find that interesting. So there are 4 fundamental forces in the universe, 4 and only 4, as far as we know. That could change, but for a while now, we've said that there are 4. The 4 fundamental forces are, from strongest to weakest, the strong nuclear force. This is the force that it does a couple things. It holds quarks together inside the protons and the neutrons, and inside the nucleus, it holds the protons and the neutrons to each other. And this is far and away the strongest force that there is. Next is electromagnetism, which will largely be the topic of the rest of the year, frankly. We'll spend most of the rest of the year doing electromagnetism. There is the weak nuclear force. So the weak nuclear force, what it does is it switches an up quark to a down quark, or vice versa, switching a down quark to an up quark. And so this turns a proton to a neutron, or sometimes a neutron to a proton. So sounds rather particular, but that is in fact very key to how the sun works. So that's the weak nuclear force. Then finally, there's gravity. So gravity is the force that binds the solar system. Gravity is the force that builds all of the big things in the universe, all the planets and stars and galaxies and solar systems. I said those in a funny order, even though gravity is far and away the weakest force. But gravity was last year kind of stuff. We're doing electromagnetism now. So when you hear electromagnetism, don't just think electricity and light bulbs and electronics and magnets and refrigerator magnets and things like that. Because look at what electricity does. It's the force that binds atoms together. So the electrons are negatively charged, the protons are positively charged. So the electromagnetic force is why the electrons want to be near the nuclei. It's also what all of the molecular bonding that goes on in all of chemistry. It's all about electromagnetic charges, electromagnetic forces. And yeah, other than gravity, all the forces you deal with in everyday life are ultimately the electromagnetic force. So all the problems we did last year involving the normal force. Well, the normal force at its smallest level is an electromagnetic interaction between things. So is friction. So is tension in a rope. Um, all of these things. So yeah, electromagnetism, this is a big idea. This is a one with everything idea. This is going on everywhere all the time. So what is a cubit? A cubit is an ancient unit of length equal to the distance from the elbow to the fingertips. Um, yeah, that's weird. So here we have this Egyptian person here demonstrating for us what a cubit is. Yeah, so a standard cubit, in scare quotes, yeah, it varied because people have different size arms and different distances from their elbows to their fingertips. But let's go with one cubit is about 45 centimeters. How many centimeters are there in a foot? Um, Well, a quick rule of thumb, a nice thing to remember is if you need to switch from metric to imperial or vice versa, 10 centimeters is pretty close to 4 inches. It's not an exact conversion, but it's pretty close. So that means 12 inches is about 30 centimeters. So then we do the whole thing with the scotch tape. So yeah, when I say 2/3 of a cubit, I really mean about 1 foot of scotch tape. So we did the whole demonstration with the scotch tape. Uh, and I'm not going to explain the whole thing because we're not actually doing this now in this video. But yeah, you did the different things with the tape. And ultimately, you would end up with one. You had 2 pairs of strips of tape, each pair containing a top and a bottom. And the top should have had the same kind of charge, and the bottom should have had the same kind of charge, which was opposite from the kind that the tops had. And yeah, by holding these pieces of tape together and keeping track of which one was which, you should have found that the tops repelled the tops and the bottoms repelled the bottoms because like charges repel. And the tops would attract the bottoms, and the bottoms would attract the tops because they would have had opposite charges, and opposite charges attract. And if you brought either kinds of piece of tape up to your uncharged arm, it should have been attracted to it. So why is this? Even though your arm has no net charge, if you bring one of the pieces of tape, and I don't even know which one it would be, the one that would have the net negative charge in it, what would happen is charge in your arm, the electrons would be repelled by this negative one, so they would move to the other side. The protons don't move towards it because the protons are kind of locked in place. That's how an atom works. That's how a solid material works. Yeah, it's the electrons that do the flowing. But anyhow, after this happened, even though your arm, so this charged sphere is now representing your arm, even though your arm has no net charge, at this point, the positive charges are a little bit closer to the piece of tape than the negative charges are. So the attraction between the positive charge is going to win because it's closer. And some of you got it to work, and when I did it, it didn't really work perfectly. And I'm still not sure why, but I'm more a theoretical guy and less of a experimentalist. So anyhow, yeah, the roots of words. So the ancient Greeks noticed that if you rubbed amber on a piece of fur, something unusual happened. The amber and the fur would attract each other, and both of them would attract dust. For this reason, actually. But yeah, the ancient Greek word for amber was electron, and this ultimately is how we get the word electricity. So yeah, it's a word. It came from somewhere. It actually comes from amber. Weird. So you could take a whole lot of materials. So glass, nylon, wool, lead, cotton, all these things, different kinds of plastic, celluloid, polyurethane, all of the things that are listed there. Rub them with fur, rub them against wool, rub them against each other, and you would find out that some things would either be attracted to the amber and repelled by the fur, or they would be attracted to the fur and repelled by the amber. So this suggests that there are 2 and only 2 types of electric charge. And you know, of course, that like charges repel and opposite charges attract. So Ben Franklin was aware of this. Ben Franklin, founding father, statesman, all these things, ambassador to France, a whole bunch of things, but also a scientist. So he was studying this stuff. He took this list, realized there were 2 groups. He called one of the groups positive, one of the groups negative. Not really based on anything. He just kind of guessed which one was which. And it turns out it would have been better had he named the charges the other way. That will come up when we start dealing with current. Just kind of this one. He guessed. It was 50-50. He guessed wrong. And it ends up being a little annoying, but you deal with it. So he got that kind of wrong. I mean, he's right that there are two kinds of charges, and it did make sense to call one positive and one negative. Just it would have worked out better if he had named them the other way. But yeah, he also noticed that when you do this stuff with the glass and the wool and the amber and the fur and all that stuff, that whenever a certain amount of charge is produced on one of the objects, an equal and opposite amount will be produced on the other one. And so the total net amount of charge produced is zero. So this is the law of conservation of electric charge. Electric charge can neither be created nor destroyed. Charge is conserved. And yeah, in physics, we love the conservation laws. They end up being very useful ideas. And we give Ben Franklin credit for this idea, the law of conservation of electric charge. So Coulomb's law. This is Charles Augustin de Coulomb. So this states that the electric force between two charges, Q1 and Q2, is proportional to the square of their separation d. So this formula here, F sub b is equal to K Q1 Q2 divided by d squared. So yeah, for whatever reason, the symbol for electric charge is a Q. Sometimes lowercase, sometimes capital Q. You may notice that the word charge doesn't contain the word Q in it, but that's how it does. That's how we do it. So sometimes, ignore this slide, you will see F sub b written as 1 over 4 pi epsilon naught times Q1, Q2 divided by d squared. It's the same thing because of what K, that's Coulomb's constant, is equal to. Ignore that. I'm just showing you this because when you see this in the physics in college, you might see it this other way. We're just going to use K. We're not going to use 1 over 4 pi epsilon naught. So if you're looking at this formula, hopefully it reminds you of a formula we learned last year because it has a very similar form to Newton's law of universal gravitation. So yeah, if we're looking at this top one, the force is equal to some constant times first thing times second thing divided by the distance between the things squared. And that's also how the force of gravity works. Some constant times first thing times second thing divided by the distance between them squared. So this is an inverse square law. This is a consequence to living in 3 spatial dimensions, is you end up with a lot of inverse square laws, which I didn't really explain in the lecture, and I'm not going to explain now, but it is, inverse square laws are a consequence of having 3 spatial dimensions, x, y, and z. So if you're looking at Coulomb's law here, so this is your basic law for electrostatic force. What would happen to force electric if one of the charges were doubled? F sub b would go up by a factor of 2. So if we keep everything the same, except we're going to double one of these Q's, what effect will that have on F sub b? It gets doubled as well. How about if we keep everything the same? Sorry, we're still using this formula. If we keep everything the same, but we double the distance between the things, what effect will that have on F sub b? So we're doubling the number that's in the denominator, and it's getting squared in the denominator. So that means F sub b is going to go down by a factor of 4. So we say that F sub b is inversely proportional to the distance between them squared. That's why it's an inverse square law. It is directly proportional to the size of the charges and inversely proportional to the distance between them squared. So something about the electric force compared to gravity is the electric force is sometimes repulsive and sometimes attractive. So if your charges are the same, you get a repulsive force. If your charges are opposite, you get an attractive force. Gravity doesn't work that way. Gravity is always attractive because mass is always positive. You can't have a negative mass. Yeah, I won't go down that rabbit hole. You can't have a negative mass, although you can have a positive or negative charge. So yeah, this is one way Coulomb's force and the gravitational force differ. So if we're looking at the constants, this little k versus this big G, little k is a very big number. It's something times 10 to the 8th newtons meter squared per Coulomb squared. I'm sorry, sometimes 10 to the 9th. I feel like I said 8th. Something times 10 to the 9th newtons meter squared per Coulomb squared. Comparing this to the gravitational constant, that's 6.67 times 10 to the minus 11th. So the gravitational constant is a very small number. That is 1/100th of a billionth, versus Coulomb's constant is a huge number. This is basically 9 billion newtons meter squared per coulomb squared. So this is why the electrical force is much stronger than the gravitational force when you're thinking of your four fundamental forces. The constant that relates to these things is much bigger in the case of the electric force. So the SI unit of charge is the Coulomb, C. So if you're using K, that number, 8.988 times 10 to the ninth newtons meter squared per coulomb squared, you've got to be using the SI unit coulombs. Although lots of times this chapter and in later chapters, we're going to be using elementary charges, E. So E, not Euler's number E, not the root of the natural log, but E, the elementary charge. So this is the charge of a single proton, and the negative number is the charge of a single electron. E is 1.602 times 10 to the minus 19th coulombs, which means that a coulomb is therefore 6.242 times 10 to the 18th elementary charges. So the first person to measure the charge of the electron was in 1909. It was Robert Millikan, this guy over here, standing next to another giant of physics over here, Albert Einstein. So here's this slide. Your quantity is electric charge. Its symbol is Q, sometimes lowercase, sometimes uppercase. The SI units are coulombs, although sometimes you use the elementary one. An electric charge is a scalar. It can be positive or negative, but it doesn't have a direction. Electric charge isn't up or down. It's positive or negative, but it's not, west. It's not left. Just positive or negative. So Coulomb's law. What's the force of a 3.5 Coulomb charge acting on a 2.5 Coulomb charge at a distance of 0.750 meters? So 3/4 of a meter stick. Is it attractive or repulsive? So what are we looking for? We're looking for the force. It will be in newtons. And the direction. This one will be a repulsive force because I have a positive charge, and a positive charge, like charges, repel. So you put in all the numbers. So there'll be a lot of calculator work. You put in all the numbers, and you get this number. The electric force, or the Coulomb force, you can also say, is 1.398 times 10 to the 11th newtons. So that's a very big number. That's 1.400 billion newtons. That's a huge number. These are the reason that that's such a big number is coulombs, like a single coulomb, is actually a pretty big amount of charge. Like 1 kilogram is a small amount of mass. 1 coulomb is a ton of electric charge. You don't often deal with numbers this big, that amount of charge in the problems we'll be doing. How about what is the force between a proton and an electron separated by a distance of 120 pm, which is picometers? So 120 times 10 to the minus 12th meters. Is it attractive or repulsive? So we want the force. It will be in newtons. The direction, this one will be attractive because a proton has a positive charge, an electron has a negative charge. So opposite charges attract. So you put in the numbers, and you end up with this. Force electric is equal to minus 160 times 10 to the minus 8th newtons. Now, a note about that. So my answer, I ended up with a negative number. The calculator gave me a negative number because at this point, I multiplied a positive times a positive by a negative, and then divided by a positive squared. So you ended up with a negative number. This is an accounting thing that you're going to have to deal with all throughout this and subsequent chapters. Because electric charge can be positive or negative. Sometimes you'll get a positive number. Sometimes you'll get a negative number. My advice is always use the positive number. So talk about the magnitude of the force and keep track of the direction of the force separate. So in this case, I gave you the positive number and I said it's attractive. It gets confusing if you say it's a negative force and attractive, because negative attractive kind of sounds like repulsion. To keep it straight, you need some kind of accounting principle to stick to. I say always go with the positive number for the magnitude of the force and keep the direction, attractive or repulsive. Keep that one separate. So to review quickly, what is the symbol for electric charge? It's a Q, strangely. What is the SI unit for electric charge? We will usually use the Coulomb, named after this guy, Coulomb. The other useful unit for electric charge is the elementary charge. I should change that from fundamental charge. If you say fundamental charge, people know what you mean. Elementary charge, the charge of a single proton or electron. And what is the law of conservation of electric charge? Well, the law of conservation of energy is that that thing can't be created or destroyed. So, yeah, Ben Franklin is the one who came up with the idea. First, kind of wrote down the idea that electric charge can neither be created nor destroyed. So, when you have static charge, you're rubbing the balloon on your hair or on your wool sweater or doing something like that. You're not creating charge, you're separating charge. You're going from something that's neutral to having a bunch of one kind of charge in one place and an equal amount of the opposite charge in another place. So the net amount of charge remains the same throughout because electric charge has to be conserved. That's it for part one of the slides. So hopefully you found that helpful.